We bought Radio Shacks. We had Radio Shack computer Model 3s before the IBM came out. No, it was 8088. The Radio Shack used the Z80 processor. So these are other conductors. They're not good conductors. Tungsten we use in light filaments. Nichrome used in electrical heaters. So some of these are metals, but they're not good electrical conductors, and we want that, right? So I've got an electric heater, and it's got that wire in there. I want that wire to have resistance so it'll generate a lot of heat. Copper is highly conductive. It's inexpensive compared to gold and silver. It's ductile, malleable, and resists corrosion and fatigue when compared to silver. Silver oxidizes real fast. Anybody that says silver plateware knows they constantly have to do what? You have to polish that thing. I mean, you leave that thing up for a week or so, and it's already started to do what? It started to corrode. Copper does corrode, but it's got a little longer. Aluminum is cheap and light, does not get along with copper. So we cannot crimp aluminum and copper together because they fall into the categories of dissimilar metals. Dissimilar metals will leave each other up. They will. So if you ever try to mix aluminum and copper, so if you ever had the opportunity to work for Alabama Power, and you see when they drop their copper down and hook it up to the aluminum company, or copper on your house and aluminum, they put this paste inside there. It's an anti-oxidation paste that you're supposed to use on aluminum. So my son's got aluminum. His house is pretty old, and when they wired his house, they wired it with aluminum. I told him about the paste, but he still won't do it. He buys aluminum. You can still buy aluminum sockets and everything. So that's what he does. But as long as you put that paste on there before you mix copper and aluminum, you'll be okay. Sets up electrolysis. A combination of metals, we call these alloys. So we do mix copper with other metals to improve the characteristics. A lot of times they do it to help with reduction, but also they do it to help with oxidation. And you'll see this a lot on very small wires. So you'll have a conductor that's copper, but it looks like it's made out of silver or but it's actually just an alloy of copper. And of course, silver and gold, we use these as what? Plating. So what determines the resistance of an electrical conductor? That sounds like a good test question, right? The length, the size, the material, temperature. So those are the four things that determine that. So the material it's made from, the size or the area of the conductor. So when we talked about the size, it's actually the area, right? The length of the conductor, and of course the temperature. And so as resistance goes up, its temperature increases on metals. Everybody okay there? So we've already talked about that. So what we do, and this is what you got in your hand, we have what we call the American wire gauge. And this guy's been around for years, and this is still what we're using here. The American wire gauge, of course, is based on inches. The European wire gauge uses basically the same thing, but theirs is gauged on millimeters, right? And it's kind of strange, and I'll show y'all the formula, but it's no thing that we need to do. But the larger the gauge number, the smaller the size. Are we okay? So this is the American wire gauge. We used to have one of these. I can't find them anymore. But somebody took it. I guess they wanted it. But basically, the numbers, you can see the bigger the numbers. So this would be what we call a aught. We don't call it we don't call it a zero. We call it an aught. We have a double aught, a triple aught, and a 4-aught that or 3-aught that we come up to. But you can see this is the actual diameter, and this would be the wire. So the American wire gauge deals with round conductors. Deals with round conductors. And the larger the number, the smaller the diameter of the wire. Everybody understand that? And this is American wire gauge. What I've gave you there. Here goes one. So this is a typical American wire gauge. This wire gauge that we have goes down. What I gave you goes down to a gauge number 50. Yeah, little fun thing. And it goes all the way up to what we call the 4/0. 4/0 is the largest that the American wire gauge covers. So anything above that is given in what we call KC mils or MCM, and we'll talk about that in a minute. So this is the gauge. This is the gauge number, and this is the actual diameter of the wire itself. So here we use a lot of 22 gauge wire. So that would be about 0.025 or 224.5 milli-inches, right? Everybody okay? Yes. And this is the formula right here for calculating the diameter given the gauge number. So this would be the gauge number over here that you would put in. And you could punch this in, and this would give you the diameter of the wire. But we don't need to know that because we can look it up, right? We have what we call circles and square mils. So a circular mil is basically a round conductor that has a diameter of 1 milli-inch. And y'all know what 1 milli-inch is, right? What would that be? It'd be that many inches, right? 1 milli-inch. A square mil, and we don't get into square mils very often in this class, but that would deal. So we have different ways that we can make conductors. We're predominantly dealing with round conductors. But if you ever look at a printed circuit board or at tabs and stuff like that, then these conductors might be what? They might be a square, or they might be a rectangle. So this is the guys that we run into on printed circuit boards. We call them foils, or they're called traces. So we have square conductors there, but just about all the conductors that we'll deal with are going to be round. So we're going to be dealing with what we call circular mils, right? Are you okay? And I need to erase my ink because I wrote that up there and then it's on the slide. Are we okay? So these are the three basic conductors: square conductor, rectangular conductors, and round conductors. And of course, we deal primarily with the round conductors. Are we okay? The area of a rectangle is equal to the length times the width. And of course, the area of a square is equal to what? Well, it's equal to any side square, yeah. Yeah. It's equal to any side. It's equal to any side square because that's the length times the width. It's just that on the square, your length and the widths are the same. How do we calculate the area of a circle? Huh? Yeah. You hear what Charles says? Yeah, so the area of a circle is equal to pi times the radius squared. And what is pi? No, that's not. Some number somebody made up. So how did they come up with pi? Pi is it's an unreal number. It never repeats. How did they come up with pi? Well, a circle has two things. It has this guy that goes around the outside. What do we call this? No, that goes around the outside. No, we call this the circumference. And a line that goes through the middle and touches both sides, we call that the what? What do we call that line? We call that the diameter, right? If you took a string or something and you measured, if you could measure the length of the circumference, so if you could take the circumference and lay it out like that, and divide that by the length of the diameter, it would always come up and give you 3.141596, and it would go on forever. So pi is the ratio between the circumference of any circle and the diameter, no matter what size circle it is. So if the earth was a perfect circle, they could take the circumference of the circle, they could divide it by the diameter, and it would come up and give you 3.14159, and it goes on. They had a little guy, a little old tiny kid, I think it was on Steve Harvey, that could quote pi out to like 50 digits, 50 decimal points. But pi is a non-repetitive number. It goes on forever. Nobody knows how far it goes. And so far, it's never fell into a what? Into a repeating pattern. So that's what you're doing. You're taking the length times the width, basically. But then you, so this would be the radius squared. We also come up and we can do different ways. So a circular area would also equal to pi, and then I could say times the diameter divided by 2 squared, right? That would be legal too, right? Because the diameter is, the radius is 1/2 of the diameter. So if I divide the diameter by 2, and then I square that, that's going to be the radius squared. Y'all understand that? Or I could go ahead and square it. I could say this area would be equal to pi. Then I could say, if I went ahead and squared it, I got it in a minute, guys. Then I could say, if I square the diameter squared divided by 4 times pi, that would be exactly the same thing. Are you okay? Same thing. Now, of course, I know from math that I could come up here. This is actually pi diameter squared divided by 4. That's the same thing, right? Understand that? Or I could come up and split out this out. So I could say this could be equal to the diameter squared times, I'm sorry. Yeah, it would be pi, right, divided by 4 times the diameter squared. That's still the same thing, right? Understand? Or I could say CA is equal to 3.14 divided by 4 times the diameter squared. Or I could say the area is equal to the diameter squared times 0.785. So if you put 3.14 and divide it by 4, you'd give up 0.785. And to me, that's a lot easier to remember than trying to remember all the formulas. So we can calculate and that's not 2 times. Let me make sure y'all understand that. This is still the diameter what? So you'll see this formula every once in a while. Well, they'll say diameter squared times 0.785, and that's all. That's just doing what? That's just doing all that, and coming up with a number. So diameter squared times 0.785, this would give you the area of a circle. And that's what that's what I've got in my head right now, right? So we teach this in fluid power, by the way, because when you calculate the force on a cylinder, you multiply the pressure times the area. And all your cylinders are round, so and when they give you the cylinder, they give you the diameter. They don't give you the radius, they give you the diameter. But if you take that diameter and square and multiply it by 0.785, that gives you the area. So. Why ain't it erasing? The area of a circle rectangle is equal to the equivalent square area, length times width. Calculate the circular mill area of a circle into its equivalent square area. You multiply the diameter squared times what? 0.785. Y'all know where the 0.785 came from now, right? Are we okay? Convert square area into circular mill area, we divide by 0.785. So a circle has a diameter of 0.0818. Well, what would be the equivalent square area? So here I'm multiplying times this. Here I'm dividing by that. So what would you think it would be? Just square it. Just square that number, right? And so what we do is we call this, if I take the diameter squared, then that's going to give me what we call the equivalent square area, right? You understand that? So this is one of the ways we rate wires. Are you okay? Yes or no? So all we do is what? I don't have the answer, but I do have my calculator. Square that number. That's all you have to do is just square the diameter. So if you square the diameter, you come up with the what we call it the circular mill, and we'll look at that in a minute. Let's see where I'm at. Two methods are used to represent the size of a conductor. We have what we call the American wire gauge number, and then we have what we call circular mills. This is the circular. Okay? Okay. Both methods give an indication of the diameter of the conductor. We pronounce it mil, M-I-L, we pronounce it mil. Right? It is short for the metric prefix for the equivalent of 0.001 inches. This is just nice enough stuff. To go from diameter mils to, we multiply by 1,000. Circular mill is, I don't know why we're not there yet. Let's go to the next slide. Okay, so this is what I want to do. Circular mill cross-sectional area is equal to the diameter of the circular conductor squared. Okay, so if I wanted to look at this one, I would come down here. What would be the circular mills for an 8-gauge wire? So what I do? Let me get my calculator back up here. So an 8-gauge, what's the diameter? No, we want inches over here. We deal with inches over here. 0.128, right? So I'd say 0.128. And then I'll do what? Then I'll square it. This would be circular mills. So that would be circular mills. Now, yeah, what we call circular mills. It's actually equivalent square mill. It's actually the equivalent square mill area, but we don't call it that. We call it circular mills. So when I look at, so this is the American wire gauge I gave you. This is another American wire gauge. Now, normally what we do, we'll show y'all when this circular mill area actually comes into play, or circular mills. I think it's this one. It might be. I got several ones over here. almost have it open in my room. So here's a, what do we say? 8 gauge. Okay. And it says 16.509, but this is not circular mills. This is what they refer to. Can y'all see it up here? KC mills. Now, so KC mills is that we take that answer that you just got and we move that decimal point to the right 3 times. So what did we get? Or we multiply, if I had a calculator, I'd multiply it by 1,000. So that's my answer. I'd come over here and I'd say times 1,000. And then what that would be, this would be what we call KC mills. Y'all understand? So this is the other way that we give the size of a wire. So the size of a conductor, a round conductor, we give it 2 ways. We give it either as a number or we give it as in KC mills. We don't use circular mills, we use KC mills. This is also the old method they used to call was MCM. It's uppercase, MCM. Well, uppercase is well, you're thinking mega. I'm thinking about the what do they call it? Representing numbers with Greek letters. The Greek number system is the Greek. Yeah. Well, M is equal to 1,000. Oh yeah. Yeah. So another method, you'll see some of these manufacturers. The old method used to be MCM. That say this would say they would have this would have an MCM of 16 point something. The new method is KC mills. Well, what I'm saying is you're going to run into both things out there. So MCM and KC mills mean the same thing. So CM is circular mills, but M in when they number the Super Bowls. What's the number system? It's not the Greek number system. Huh? Roman numerals. Yeah, well, the Roman numerals, if you looked up the M in the Roman numerals, it's 1,000. So 1,000 circular mills. So MCM, if you see a cable rated in MCM or you see a cable rated in KC mills, those are the same thing. Everybody understand that? Thanks. So over here we would say, and you can see, now what we do, and you see they go all the way up to 4/0. And yours don't give circular mills. So normally what we do is we rate cables up to 4/0 using the American wire gauge. Any cable any conductor that's bigger than a 4/0 will be in KC mills. So that's where you're really going to run into KC mills on things above what? Above 4/0. For sure. You still have manufacturers that are going to use these even for these conductors down in here. But standard. The problem with American wire gauge is if you don't understand the American wire gauge, and I say you need a 4 gauge, to us that means what? It means nothing. Right? You understand. But if I was to say 41.7 KC mills, then that would give me an indication. Now, if I needed to know the diameter, I would just take the square root of that, right? You understand? If I needed to know the actual diameter. If I didn't understand the American wire gauge, and I say a 4 gauge wire, I'd have to find this dang table and do what? And look it up. You understand that? It's given in KC mills. I can do that with a calculator. I just take whatever KC mill it is, right? You understand? Then I would divide it by 1,000 and I'd take the square root of it. Or take the square root of it and then shift it in my head. So you can see what advantage KC mills have, or MCM has, over the American wire gauge, because the American wire gauge, you only learn these gauges if you deal with them what? If you deal with those conductors a lot. So we know, if we're in house wiring, we know what 14 gauge house wiring is. We know the difference between 14 gauge and we know the difference between 12 gauge. We don't know the diameter, but we can look at it and tell, right? So an electrician can say, well, that's 14 gauge, right? Because that's all they basically deal with. They deal with 14 gauge, they deal with 12 gauge, they deal with 10 gauge and 8 gauge. That's about all you'll ever run into house wiring.
What about the service line going out to work? What is that like? Big stuff.
That's big stuff. That would be labeled in KC Mills. And we might look that up and say what would be the KC Mills for the down drop. Because anything greater than a 4/0, which is just smaller than a half inch, anything bigger than a half inch will be in KC Mills.
You're talking on the other side of the meter, right?
Yeah, he's talking about the down drop.
Residential electrical work, that's usually always pain in the butt. You have to deal with putting up new pipes.
No, that might be that wire is not, that wire is probably, it's, no, you're talking about, we're talking about the down drop. You're talking about the insulation.
This got conductors in it, too hot.
Well, it depends. The down drop is usually, you have your neutral coming down. It's a metal cable. And then you have your two wires wrapped around that.
You can aluminum part of the ground, you get two wires.
Yeah. But that's less than this. The down drop is usually for a house. For a house, it's not. It would surprise me if it's above 4/0. I mean, we could look it up. Even though I've ran it before, I don't remember. I haven't ran that, but I've ran it underground. Huh? Are we okay? So how do we go from diameter to KC Mills? We just do what? Square it. Multiply 1,000. If you got a calculator, if you got your head, you just move the decimal point over, right? And if you wanted to get the actual diameter, you'd move it to the left 3 times and then take the square root of that, right?
So that part is just a gauge. When you go to a circuit, you have to shift it over to the cable. Why would you switch to the cable?
Because you're dealing with these very small fractions. Why don't we say 0.0001 ounce? Okay. Well, the average person would, but if you got in with somebody that understood electronics and you start saying 0.00001, they're gonna say it's sucking on the lid. Right? You understand? Because we do with what we call engineer notation. So what they're doing is they're taking it and converting it over to milli. But we don't call it milli, we call it KC Mills. And the trade, they understand KC Mills because it says, okay, multiply by 1,000. But it's us in engineer notation using milli instead of 0.001. So instead of using 0.0168, we say 16.8. We don't say milli, we say KC Mills, right? You understand? Because it's not actually milli inches, it's circular mill areas, right? You understand that? That makes sense? So why? Because it's a lot, yeah. So understand what I'm saying? Yeah, I'm sure you do. So it's just another method of representing these real small numbers with fewer digits. And you'll see they're not going to carry that thing out this far. They're going to round it. Right? You understand that? And this stops there, but oops. And then to go to square mill area, all we'd have to do is take that and multiply it by 0.785. And that would give us the actual true area of the conductor, right? Are you okay? That's where the 0.785 came from. To convert from a decimal fraction to KC Mills or KC Mills squared, multiply the fraction by 1,000. This simply requires the decimal point of the fraction to be moved to the right. How many times? 3 times. And we learned that trick in there. Wire sizes are usually given using the American wire gauge number, diameter, millimeters, circular mill areas, and here they could be called circular KC Mills, right? Or what? MCM. Y'all understand that now, right? And then square mill areas. And this is a little math. We already know that. So if you're given the KC Mill, right, then what was the first thing you would do? The first thing you do is be divided by 1,000, and take the square root of it. Of course, we know to divide by 1,000, we would just move it to the left 3 times, right? So to multiply by 1,000, we move it to the right 3 decimal points. So let's do that. Let's convert these over. I'm going to pause this. Let's see if y'all come up with the right answer. So it will be 1.6 KC meals, 1.3 circular meal areas. 12 gauge wire would be equal to, what did I do? Was there another one over there? Oh, I'm sorry. I didn't see that one. I went from here down to there. So 12 gauge wire has a diameter of this many KC meals. What would be the conductor's diameter in diameter, right? So the diameter is given to you. I mean, all you'd have to look is up a 12 gauge wire. So what's the diameter of a 12 gauge wire?
What it is in KC.
Well, that's not the way the question's written. What would be the conductor's diameter in KC meals? If the answer's not written like that, then the answer is wrong. Because according to this, they want the conductor's diameter. So what's the conductor's diameter? So I'd look up a 12 gauge wire. So 12 gauge, what would be the diameter? What? 0.081. Okay, so that would be the diameter, right? And then what would be the KC meals? Let's go.
6.561.
Are we okay? Let's say 0.081. Then I'll square that. And then I'll multiply that times 1,000. Okay, we're okay? And then I'd multiply that by 0.785 to get the square mil. 5.15. Are we okay? So I don't know if it was like that over here. 18 mils. Yeah, that was 81 mils. That's milli-inches, right? You understand that? Okay, y'all said 0.018. That would be the same thing. So hey, the right answer was there. Are we okay?
Now, dude, how far do you want us? If this was a test, how many decimal places?
Well, if it was a multiple choice, you would choose
the
one that fits. If it was a fill in the blank, then I would tell you how many decimals. That would be part of the answer. I mean, part of the question. Are you okay? Ampacity, the amount of current a conductor can carry without exceeding an allowable temperature, allowable operating temperature, influenced by the material, the size, the installation, the ambient temperature, the insulation method, number of conductors in close proximity, and the actual current level. So when we come up here and we look at the American wire gauge, what do you notice above the resistance at the top of the column? No, at the very top of the column. It says
at 120 degrees.
At 20 degrees centigrade. Right? You understand that? And what temperature would that be in Fahrenheit? So we're going from big to little, so it's going to be what? Right? And times the temperature, 20, and then plus 32. That don't look right. This is Celsius, right? So we're going from little to big. So yeah, so we'll multiply it times 9/5. That's still not right. There's something wrong. Is it 9/5? 5 ninths and 9/5? Well,
Number 32 in there somewhere? Or,
I add that to it. I add 32. Got surface, got a 95.
Yeah, there we go. Plus 32. Yeah, so I did something wrong. So it's about 68 degrees. So if you're going from big to little, it's 9. If you're going from little to big, it's 9/5. If you're going from big to little, it's 5/9. Because if you ever looked at the Celsius scale, for every 9 on the Fahrenheit scale, there's 5 on the 5 mark on the Celsius scale. And then we add 32 to compensate to put them both at 0, right? So 68 degrees. So that means if it's above 68 degrees, what does that mean about these resistance? Are they going to be higher or are they going to be lower?
higher, this is going to be higher.
Yeah, the resistance will be higher. If it's lower than 68 degrees, the resistance is going to be lower. So anytime they give you the resistance of a wire, they're going to have to give it to you at a temperature because the resistance of the wire varies with temperature, right?
That's the 400 feet.
Down 1,000 feet. Oh yeah, this is about ohms per 1,000 feet. That's the way this thing's set up. Now, all that makes sense? So we can't, if I say, okay, what's the resistance of a 24 gauge wire? You need to say, I don't know. It's going to be somewhere, right? If it's 68 degrees in here, it would be this. If it was greater than that, then it would be a different temperature. And so this is also says it's in free air, right? Going to say free air up there on the American Wire Gauge?
Well, the next free ampacity.
Yeah, free air. Free air. And what do we mean by free air? It means the wire is uninsulated, right? Y'all understand that?
So insulated change ampacity.
Yeah. So what they did on the if I look at a 14 gauge wire, what's the ampacity of a 14 gauge wire in free air at 32 amps? But NEC rates a 14 gauge wire at 15 amps.
They allow for
They don't only allow for the insulation, they allow for everything. So as soon as I put 2 conductors in a cable, the ampacity goes down because now you got 2 wires generating that heat, right? So when you deal with the National Electrical Code, one thing when you start dealing with conduit fields, then you start reducing the ampacity for every other wire you have in there. You have to induce the ampacity of each wire because now you not only have heat generated by one conductor, you have heat generated by multiple conductors, right? So you say, okay, in house wiring, where can the wire run from? Where do they run the wires at? They run through the walls, they run through the attic, they run through the basement, right? Okay, so as soon as I go through the attic and it's in the summertime in Alabama, that's going to reduce the ampacity of the wire. If I run it in my walls, right, through the insulation, it's going to reduce the ampacity of the wire. So why NEC rates a 14 gauge wire at 15 amps? Because they've rated it for all these other situations. So as long as you don't run it over, I think 100 feet, then you can use 14 gauge wire in a 15 amp circuit. Okay. So that's why, and plus it's insulated. As soon as I put an insulator around the wire, what happens to the ampacity of the wire? It goes down. Why? Because now the heat that's being generated by the conductor can't get out, right? You understand? So when you look at and that 15 amps is with a certain insulation. And so we can buy several types of insulation we can for this wiring. So commercial might get more out of a 14 gauge wire than residential. Because usually in commercial we run individual conductors, right? You understand? We don't use a lot of cables. Okay guys, y'all take a 10-minute break. If y'all want to, y'all can hang. I think this is, this is NEC right here.
I want to do something.
You get people, they'll do that though, yeah.
House over 1,000 feet, you can call somebody anyway.
Well, you can have them, but you just gotta keep it in line. Usually those big houses like that have multiple animals. Some have multiple animals. Yeah, but you gotta understand before you take the test, you gotta have 4,000 hours of experience.
Yeah, I already have it.
Oh, really? Well, that's what it does. It teaches you how to go through all those tables and look up those codes. They get practice tests in there just to get your time down.
So when do they usually?
You used to teach it in the summer. I think it's on schedule for summer.
They would be this summer or?
Yeah, it's on schedule for this summer. I think it's night. You only do it on night. That's about the only time contract is on night.
All the time.
I get home and I have a lecture, the NEC. This is right out of the NEC code book. And this is their ampacity chart right here. And notice here's a 14 gauge wire. And then they rated it 15 amps, they rated it 20 amps, and they rated it 25 amps. What changed? Why does it change?
What?
Well, the insulation. So these are the insulations. These are, and I'll give you, there's a chart up there that shows you what each one of these codes stand for. So if I use some of this insulation, this is just TW wire. This is what we use as house wiring right here, mainly. And then what they've done, and then they've got all these adjustment factors in here. So correction factors based on NEC table ambient temperature corrections. So that means this is rated at this temperature, right? You understand? But if I run it above that, or 10 ambient temperature, 10 degrees, 20 degrees, then what we would do is if you run it below that, you multiply it by 1.56 because you can get more current. If you run it at that, or if you run it above that, so this is where we would have to direct it for temperature, right? You understand? And these are all these charts. Where the number of current carrying conductors in the raceway or cable exceed 3, then as soon as you get past 3, then you're going to have to start. So if I've got 4 to 6, I can only get 80% of the rated current, right? You understand that? And then it's got other tables in here. These are permitted ratings of dwelling units, service, and feeder conductors, which carry the total load of the dwelling. Okay, y'all see that? So this is right out of the NEC code book, where you literally have to do what? You come up with basics, but if you exceed what they say, then you're automatically going to have to. So if I ran two, according to this, if I ran two Romex cables through the same piece of conduit, that's 4 wires, and automatically I'm going to have to do what? I'm going to have to come up here automatically. I'm going to have to reduce that down, right? Y'all understand that? So that's this is right out of the code book. The new code book, 2017. They come out with a new National Electrical Code every 3 years. Yeah. Well, OSHA can change their rules anytime. NEC comes out every 3 years. And then it's usually delayed before the authority having jurisdiction actually adopts the new code book. So I don't know what code book Birmingham is running out of now. I think Jefferson County is doing electrical inspections now. I'm not sure. For a while, when they was going through all that, where they faulted and they actually stopped their inspectors and they would honor the Birmingham license. I don't know if they started it back up or not. I need to ask Floyd about that and see. Yeah, they cover them. Insulators. Insulators isolate the electrical conductor from other conductors and individuals, which are us, right? You understand that? Jackets provide additional thermal, chemical, mechanical, and environmental protection. So the jackets are on there for protection against the environment. The insulator is to keep that pushing, right? A conductor's insulator and jacket may sometimes be the same. We talked about that. Insulators, these are the way we classify insulators, by the chemical resistance, the heat resistance, the moisture resistance, and the oil resistance. So this is the way insulators are actually. These are our type insulators. We have rubber, elastomers, which would be neoprene, Hypalon, ethylene, propylene, rubber, styrene, I can't even say that. Thermoplastics, polyvinyl carbon, polyethylene. Thermal setting. These are the two primary insulators that we'll run into. It's thermoplastics and thermal settings. So thermal settings, nylon, Teflon, all these would fall into what we call thermal. Jackets and shields, polyvinyl chloride, polyethylene, polyurethane, thermoplastics, elastom. And I think I've gave y'all, I get them confused in sometimes, but we have the thermoplastic category. These are the guys I'm pretty sure that their insulation softens when we heat them. And then thermal settings, these are insulators that want to carbonize or get brittle when they heat. So thermal setting has a higher temperature rating on it than thermoplastics. So this is a typical low voltage conductor. So what we have? We have a what? Conductor, and then we have an insulator, then we have a jacket. So this is what you'll run into in house wiring in most of your conductors that will. Now the clear, look clear. It's got that little. Most people don't see that, but if you ever strip uh, what they call Romax, which is it's the 14. We call it 14.2 with the ground. That's the way they specify it. So 14.2. 14 is the gauge. 2 is the number of current carrying conductors, and then ground would be the other conductor. Right? You understand that? So if you went out here to Lowe's, that's what you want. You want 14.2 with ground. We call it Romax because that was the company that first developed this layout of the solid strand wire laid out in that. So you'll hear a lot of people call it what? Romax. This is a medium voltage cable. Now what we need to do on a medium voltage cable is a medium voltage cable and we talked about this. People don't understand, and this is the problem we have, is that when we start moving this cable and we get it around things, then what happens is that the stress on the cable moves. So when we have an insulator rated at 500 volts, that would be 500 volts around that cable. As soon as you put this thing up against something, and that electrostatic field moves to one side, it could bust. It might be 300 volts that busts through an insulator that's rated at what? At 500 volts. Does that make sense? So the higher the voltage, what we have to do is we have to equalize that tension or that push around the outside of that conductor. And so what they do is they'll come up here and they'll build it in layers. So we'll have our conductor. And then around our conductor, we'll put a semiconductor layer. And then we'll come up here and we'll put an insulator. Then they'll put another what? Semiconductor layer. Then we'll come up here and they'll put a metal shield. Then over the metal shield, they'll put a what? Jacket. I see too straight for that. And so you see what it does, it distributes that what? The electrical stress, right? This is made up of a cable we call a coaxial cable. And we have some of this back there too. It's a misname, but that's what they call it in the field. So that's one of your conductors. And the spacing between this outside conductor and this inside conductor has to be precise, because that's what sets what we call the characteristic impedance of the cable. So that's why now your cable TV uses solid strand. They don't use a stranded wire. So you use that FNC connector, and you basically that center solid strand is your middle conductor, and then that outside metal shell that you screw in is going to be your outside on your cable. So if this stuff ever breaks, you don't just twist it together because you'll screw up the characteristic impedance of the cable. You have to have special splices that you put on. Outside box, before you get into communication conductor, let's discuss gain, attenuation, and dB. Okay, so what we're going to do now, we'll start on this just a little bit, but what we're going to do is we're going to use the lab tonight. In fact, we'll stop right here right now because we got to do a couple more lectures before we learn how to use it. So what we're going to do is we're going to let y'all use the micrometers. Download my micrometers. Do you ever use micrometers?
Yep. Put the mic on the pipe and measure the thickness.
So what we do is we got 7 different conductors that you're going to come in, and you're going to measure the diameter, and then you're going to look up the wire gauge. Well, then you're great. So y'all hear that? Charles is the expert, right? Huh? What we'll do is we're going to stop the lecture right here so we can do this lab. So y'all remember what slide I'm on. And then I'll start another. where it went.